All right, today we're jumping into a paper that's been making some serious waves. It's called MemEvolve, Meta-Evolution of Agent Memory Systems, from the OPO AI agent team in the LVNUS lab.
And if you've worked with LLM agents, you'll immediately get why this is so important. The fundamental flaw right now is that their memory systems are static.
Right, so the agent can learn new skills. That's what the paper calls first-order evolution. But the system that governs how it learns is totally fixed.
Exactly. MemEvolve introduces this meta-evolutionary framework. It's a second-order evolution that lets the agent evolve both its knowledge and the memory architecture itself, all at the same time.
So it's adapting its learning strategy to the task. And the way they enable this is through something called EvolveLab.
Yeah, EvolveLab is this unified code base that breaks memory down into 4 clean modular components: encode, store, retrieve, and manage.
And the results really speak for themselves. We're talking about huge performance gains, boosting existing frameworks like Small Agent and Flash Searcher by up to 17%.
And it's not just performance. The evolved systems showed really strong generalization, both across different tasks and, maybe more importantly, across different LLMs. They even worked well on backbones like Kimi K2.
Okay, so let's unpack this. What's the core motivation here? Why is this static memory architecture such a big problem?
Well, think about all the self-evolving agents we have now. They're great, but they all rely on these handcrafted, manually engineered memory systems to, store their experiences and learn from them.
And the assumption is that one size fits all, that one architecture is going to work just as well for deep research as it does for, say, writing code.
Which is just not true. A memory system that's been fine-tuned for retrieving reusable APIs, which is great for web browsing, is probably going to be pretty limited for complex scientific reasoning.
And vice versa, I imagine. A system built for self-critique and abstract thinking might be way too slow or clunky for a task that needs rapid tool use.
Exactly. The variability of tasks demands that the memory design itself has to be task-aware.
The paper has this really great analogy for it. They talk about a mediocre learner. That's just your basic LLM, no real memory, just rote memorization in its context window.
Right. Then you have the skillful learner, which is where we are now. These agents have fixed, predefined memory systems. They're learning skills, but their learning strategy is rigid.
But the goal, what MemEvolve is aiming for, is the adaptive learner.
Yeah. The adaptive learner is someone who changes how they learn based on the subject. You wouldn't use the same strategy to learn a language as you would to learn physics.
You'd use flashcards for one, and maybe abstracting formulas for the other.
Precisely. So the formal challenge they're tackling is, how do you get a memory system to not just help the agent evolve, but to meta-evolve its own architecture for better performance and generalizability? It's a huge question.
And to even start answering that, you need a common language to describe memory. Which brings us to EvolveLab.
EvolveLab is really the foundation of this whole work. It's a unified code base that takes memory architecture from this kind of opaque, custom-built thing into a standardized, systematic design space.
So they actually went back and re-implemented 12 different memory systems, like Voyager, Expel, all the big ones, using this new modular framework.
They did, and that's what allowed them to define the memory genotype, this 4-part architecture they call Omega. It's the blueprint that the meta-evolution can actually work on.
Okay, so let's walk through those 4 components. The first one is encode, or E.
Right, so encode's job is to take the agent's raw experience, all the messy stuff from interacting with the environment, and turn it into a structured representation.
And a simple system might just compress the text, but an evolved one could do something much smarter.
Much smarter. It might use the LLM to pull out general lessons or figure out why something worked or failed. The encoder itself becomes a learned part of the system.
Okay, so after encode, you have store, or U.
This is the back end. Once you have that structured memory, where does it go? A simple JSON file, a vector database, a knowledge graph. The store component defines the long-term persistence layer.
Then there's retrieve, R. This is how the agent gets information back out.
Yeah, this is the context-aware recall. When the agent faces a new problem, what does it pull from memory? Is it a tool? Is it a similar plan it's seen before? How does it filter out the noise?
And the last one, which feels like it's often forgotten, is manage, or G.
Oh, it's so important. Manage is all the offline stuff. Consolidating memories, abstracting knowledge, and crucially, selective forgetting. Without it, the memory just gets bloated and useless over time.
And because they define this framework, systems that seem totally different on the surface, like SkillWeaver and Expel, can actually be described using the same EURG components.
That modularity is what makes the whole meta-evolution possible. Which brings us to the MemEvolve process itself. It's a bi-level optimization. You have an inner loop and an outer loop.
Okay, so the inner loop sounds like the standard agent learning process. Is that right?
That's right. It's called experience evolution. You take a candidate memory architecture, you let the agent run with it, and it generates experience. The memory gets populated according to that architecture's rules.
And the key here is that they're tracking feedback on more than just success or failure.
Exactly. For every trajectory, they record task success, but also token consumption, the cost and latency, so the delay. It's a multi-objective feedback signal.
And that rich feedback is what fuels the outer loop, the architectural evolution.
Yep. This is where the memory system learns how to learn. The meta-evolution operator takes that feedback and uses it to update the architecture itself.
So how does it decide which architectures are better?
The first step is architectural selection. They use what's called non-dominated sorting, which is basically Pareto optimization. They're not just looking for the highest performance.
They're looking for the best bang for your buck. The best performance for the lowest cost and delay.
Precisely. It prevents the system from evolving some monstrously expensive architecture that solves the task by brute force. The top K candidates from that Pareto front survive.
But it's not just survival of the fittest. There's another step.
This is the real innovation. Diagnose and design evolution. It's not just randomly mutating the memory components. The system actually analyzes the failures of the top architectures.
Wait, really? So it looks at a failed run and says, okay, retrieval was fast, but the information was too vague.
That's exactly it. It generates a structured defect profile that pinpoints the bottleneck. Maybe retrieval failed, or the memory was too long, or abstraction was poor.
And then it uses that diagnosis to intelligently redesign the components.
Yes. Conditioned on that specific defect profile, the LLM proposes targeted modifications to the E, U, R, or G modules. It's an empirically grounded, targeted update, not a blind guess.
That makes so much more sense. It's a virtuous cycle. Okay, so this all sounds great in theory. Let's talk about the results. Did it actually work?
Oh, it worked. The numbers are really strong. Using GPT-5 Mini as a backbone, the Flash Searcher agent, once it was augmented with a MemEvolve architecture, saw its accuracy on xBench jump from 69% to 74%.
And on GAIA, which is a notoriously hard benchmark, it even outperformed some multi-agent systems.
It did. It got an 80.61% pass at 3, which beat systems like OWL Workforce.
But what about the cost? I mean, that's what I was waiting for. Did the API costs go through the roof?
That's the most stunning part.
No.
The API costs were comparable to the no-memory baseline. On GAIA, it was basically identical. The architecture is evolving to be smarter, not just bigger.
Wow. Okay, that's a direct result of that Pareto optimization you mentioned.
It has to be. They are explicitly selecting for efficiency.
So what about generalization? An architecture evolved for one task isn't that useful if it's brittle.
They tested this really rigorously. They evolved memory systems on a synthetic task called Taskcraft, and then just dropped them unchanged into real-world benchmarks like WebWalker QA. And they still saw consistent gains, around 3.5 to 5%. It suggests the process is finding general, robust principles of memory design, not just overfitting to one environment.
That's cross-task. What about cross-LLM generalization? That seems even harder.
And maybe even more important. They ran the evolution on GPT-5 Mini, then took the final, evolved memory architecture and paired it with completely different models like DeepSeek and Kimi K2.
And it still provided a boost.
A huge boost. Kimi K2's performance on WebWalker QA improved by over 17%. This is massive because it means you can discover an optimal architecture with one powerful model and then deploy it with a cheaper, faster one.
It decouples the architectural design from the model itself, and this is where the human design baselines fell apart, right?
Completely. A system like Expel, which is great in some contexts, underperformed on all 3 of the challenging long context benchmarks. It just validates the whole premise. Static architectures can't keep up.
So let's get into the qualitative side. What do these evolved architectures actually look like? What kind of changes did the system discover?
Well, the biggest trend was a move towards more agentic involvement. The LLMs started making decisions about memory that were previously just hard-coded pipelines.
Can you give an example?
Sure. One of the early winning architectures evolved to store memories at 4 different levels of abstraction. And, this is the cool part, it also evolved an LLM-based meta-guardrail for retrieval.
So it wasn't just doing a simple vector search.
No. It would do the search, And then have the LLM take a look at the results and actively filter out anything irrelevant or misleading before it went to the agent's main context.
That's a pretty sophisticated mechanism to evolve on its own.
And they got even more complex. A later system they highlight, called Cerebra, learned to do two things at once: distill reusable tools and abstract general knowledge.
Yeah, it also started doing its own memory maintenance.
Yeah, proactive maintenance. It incorporated periodic mechanisms for pruning and consolidating its knowledge graph. It learned that to stay efficient, you have to clean house, essentially. It's a lot like how biological memory works.
There's a great example in the paper with a really complex GAIA task finding, a Wikipedia revision count for a game.
Right. And the evolved memory system was incredibly adaptive. At the start of the task, it gave the agent high-level planning advice, breaking the problem down.
But then as the agent got closer to the answer,
It switched. The memory retrieval started providing very fine-grained tool use suggestions, like the exact MediaWiki API call needed to get the data. It shifted from strategy to tactics seamlessly.
it even showed what they called predictive behavior at one point, right? It anticipated where information might be hiding.
It did. On an XBench task, it guessed that the info it needed might be in the image captions on a travel website and guided the agent to look there. And it was right. That's the kind of adaptive intelligence you get when the architecture itself is fluid.
So really, MemEvolve isn't just an improvement. It feels like a new direction, evolving the architecture itself to build smarter, more adaptive learning.
I think so. What this work really does is provide EvolveLab as a standardized substrate. It's moving agent memory research from a world of custom one-off designs into a systematic, automated, and meta-evolutionary path.
Which means the whole community can build on this and iterate much faster.
For sure. And it leaves us with a really interesting thought. If an agent's memory and learning strategy are constantly optimizing themselves, if that core cognitive framework is always in flux, it raises a critical question for all of us building these systems.
Which is,
When the memory architecture isn't hand-coded by a human anymore, but evolved by an optimizer, how do we audit it? How do we make sure it hasn't converged on some weird, brittle solution that looks efficient on paper but fails in unexpected ways? You really have to understand that Pareto front. But for anyone who wants to dive in, the EvolveLab code is all open source on GitHub.